Hello, today we are going to look at the conjugate root theorem, and we're going to look immediately at what that means. So we know what a root of something is. It's where it crosses the x-axis or where y would be equal to 0, and we know that a conjugate is where if we had, say, this pair we have here, if z is equal to minus half plus I, the conjugate would be minus half minus I. We change the sign of our complex part. And we'd also see this in our work with surds. Now, if we take the equation y is equal to 2x squared plus 2x plus 5, and we go to find its roots, we'll find we can't factorize it. So if we go to the minus b formula, we work down through our problem, and what we will find at the end is we end up with x is equal to minus 2 plus or minus 4i all over 4, which simplifies down into x is equal to minus a half plus I, or x is equal to minus a half minus I. Now what should jump out at us here is that the minus b formula automatically gives us a conjugate pair, because we have plus or minus the imaginary part. Plus or minus the imaginary part is exactly what we do to create conjugates of our complex numbers. So this tells us, because the minus b formula is where we're getting these roots from, where we're getting our complex roots from, this tells us that complex roots are always going to come in conjugate pairs. But there's a caveat. This is only true, and it's very important that we know that it's only true because it's come up on the exams. This is only true if the coefficients that we're dealing with in our equation are real. If we had something like 2 plus I times x, or just I times x squared, anything involving complex numbers as the coefficients of our equation, this does not hold true. This is only true for real coefficients. But if we can combine this fact for appropriate situations where we have real coefficients, if we can combine this with the factor theorem, where if we know the root of an equation, we can rearrange to get the factors and thereby multiply up to get the original equation, we can combine these two things to solve an awful lot of problems where we're looking for equations of complex equations. So let's put this into practice. Z is equal to 2 minus I is a root of az squared plus bz plus c, where a, b, and c are real. Find a, b, and c. Now I can see that this is a quadratic type equation. I have z's instead of x's because I'm dealing with complex numbers. And I'm told that a, b, and c are real. And that means I'm able to use the conjugate root theorem, because a, b, and c are real, and only then. So what does that mean? It means I know one of these roots. I know that z is equal to 2 minus I is a root, which means I automatically know that the conjugate, z bar, is also a root. So now I have my two roots. Now what I'm going to do is use my factor theorem and say if I know that I have a root, I can rearrange it, get it equal to 0, and then that will be a factor. So rearranging, I'm going to have z minus 2 plus I is equal to 0. Via the factor theorem, this is a factor of my equation. And we would have done this in algebra. And again, rearranging this, I'm just going to call this z. So if we rearrange here, I have z minus 2 minus I is equal to 0. These are my two factors of my quadratic. If I multiply these two factors together, I must get my quadratic. So then this is just multiplying out brackets. I multiply my factors together. This is identical to factor theorem problems that we would do in standard algebra. There is absolutely no difference. Minus 2. I'm going to write this out for you and come back to you. So when I've multiplied out my brackets, I get this long list, and this is a very important case where we'd want to be underlining our like terms. And we have that is going to be e plus 1, but that's just going to take a second now. So that's a lot of the stuff that is going to collapse down. So I have a minus zi and a plus zi, so they are going to sum to 0. I am going to have, I'm not going to do that because it will make it harder for you to take down notes. So I'm going to have some stuff that sums to 0, and I'm going to have minus I squared is going to go minus 1 is going to be plus 1. So my next line comes down to z squared minus 4z. That sums to 0. That's dealt with. Plus 4. It sums to 0. That's summed to 0. Minus 1. Is equal to z squared minus 4z plus 5. So that is my equation. And then what are my, remember that I was looking for a, b, and c. So a is 1, it's the coefficient of z squared. B is minus 4, and c is plus 5. So that is my equation. So that is my work for this question. And then part 2, I have actually written in incorrectly. If is a root, is what that should say. So how do I show that something is a root? Well, it should make the equation equal 0. If I sub in this value of z into my equation, it should make the equation equal 0. So let's try that. Z squared minus 4z plus 5, and it should equal 0 when I sub in z is 2 minus I. So you just sub it in as you would again with any normal piece of algebra. So complex numbers, there's a huge amount of overlap with what we already know in algebra. So square the first by the second and double it. Square the second. Sorry, no square there. Minus 8 plus 4i plus 5 is equal to 0. Now I'm going to square that. So I squared is minus 1, so 4 minus I minus 1 minus 8 plus 4i plus 5 is equal to 0. Gather like terms. So I have minus 4i plus 4i is going to sum to 0. And then I have 4 plus 5 is 9. Minus 1 minus 8 is minus 9. So I end up with 0 is equal to 0. Therefore, I have a root. And that is the beginning of what we need for the conjugate root theorem.